So, good afternoon, all. Can you all hear me?
Yes, we can.
Yes.
Okay. We only have 90 people in today's class. Okay. Hopefully, today's lecture won't have the network connections we had in the last class. I'm in a much better place. So today we're going to talk about, in the next series of lectures, we're going to talk about learning neural networks. So the topics are, for the day, are the basic problem of learning. And we'll talk about the perceptron role for learning individual perceptrons and how it's not applicable to multi-layer perceptrons. There are some slides here on greedy solutions for classification networks. These are called algorithms called Adeline and Madeline. I expect you to look through the slides for these topics, but because they'll appear in the quiz. And we'll briefly touch upon empirical risk minimization and function optimization, and those will be the topics of the next lecture. So for a quick recap, here's what we know. Neural networks are universal function approximators. What we mean by this is that regardless of the function, you give me a function, I can always compose a neural network that can compute it. So they can model any Boolean function, they can model any classification boundary, they can model any continuous valued function, all to arbitrary precision. All of this is only possible, as we saw in the last class, provided the network satisfies some minimal architecture constraints, meaning it should have a minimum width and a minimum depth. And networks that have fewer than the required number of parameters may not be able to perform the approximation that we require. But provided the network has sufficient architecture, it is technically possible to model the function that you want to. We also saw that in all of the AI tasks that we considered early on, like voice recognition, image captioning, or playing games, or pretty much any task where we apply neural networks are basically functions that take in an input and compute an output. So since neural networks are functions, we need some way of representing these functions, but we need to represent not just the functions, but also the output, the input and the output. These are mathematical objects and they work on numbers. So the questions we have to answer is, now when we speak of tasks like voice recognition or image captioning or playing games, the voice signal, images, and the games are not naturally numbers. And so we have to, and so also transcriptions, captions, and a prediction of a game move is also not naturally a number. So we have to ask, how do we represent the input in mathematical form? And how do we represent the output in mathematical form? And finally, once we have something numeric going in and something numeric coming out, then we can build this box in the middle that transform what comes in to what goes out. But then the question is, how do you compose this network that performs the requisite function, the function that performs the task we're interested in? So for today, we won't be talking about how to represent the input and output. We're going to focus on composing the network that performs the necessary function. Now, we saw earlier that the basic unit in a multi-layer perceptron is the perceptron. So in the generic setting, the inputs are real valued. The unit computes an affine function of the inputs. So which is to say it computes a weighted sum of the inputs and a bias. And this affine value, Z, which is passed through an activation function to compute the output of the perceptron. The basic perceptron that we saw assumed a threshold activation But activation functions are not necessarily threshold functions. They can be anything else, like a sigmoid or a rectified linear unit shown by this red curve here, or the softer version of it shown by the blue curve here, or pretty much any other function. So sometimes explicitly representing this bias over here can get tedious. So we will take a shortcut and simply assume that whatever input we have has an extra component whose value is pegged to 1. And then the weight associated with this extra component simply becomes the bias. So this is just a different way of representing a perceptron where we don't explicitly show the bias. So in my lectures, anytime I show you a perceptron without an explicit bias like this one, it basically implies that I'm implicitly considering an extra component to the input that accounts for the bias. So is this bit clear to you folks about how this value of 1, this extra component pegged to 1, represents a bias? Okay. So now we are speaking again, going back. These are all of these are all mathematical operations, regardless of whether you're performing voice recognition or image captioning or playing games. Basically, you have something going in and something coming out, and you have a function which takes the input and computes the output. So we need to make some assumptions about the function. We're going to assume that the function is being modeled by a feed-forward neural network. What do I mean by a feed-forward neural network? It means that there are no loops. So an input proceeds through the network and eventually gets to the output without ever revisiting a neuron. So once a neuron processes an input, it's done with that input. That value is not going to travel in a circle and come back to the neuron. It's just going to go left to right in my figure. We also do have loopy neural networks, but that's a future topic. So part of the design of this network to model whatever function we are interested in is the architecture of this network. How many layers the network has, how many neurons it has in each layer, and so on. For now, we're not going to get into that. We're going to assume that the architecture of the network is capable of representing the specific function that we're trying to compute. So once you model it, once you think of it that way, then we are now given a network and we're given its architecture. And within the network, each neuron is basically one of these perceptrons which gets a bunch of inputs and computes an output. The parameters of each neuron are the weights and the bias for the neuron. And these are going to be different for each neuron in the network. So the entire network is now this parametric function where the set of parameters for the network is the union of the parameters of all of the perceptrons in the network. So it's the complete set of all parameters, all weights, and all biases of all the neurons in the network. So the network itself can be represented like so: f of x semicolon w, where x is the input and w represents the set of parameters of the network. The behavior of the network depends on w. You can change the behavior of the network by changing w. So moving on. So is that all clear? We're going to just work on the basics. Any questions? Okay, that's the easy bit. Now, what we've seen is that a multi-layer perceptron can represent anything. Meaning you give me a function and I can construct a multi-layer perceptron to compute it to arbitrary precision. Again, assuming that the architecture of the network is given, what do we mean by constructing a network? What do you think we mean when I say I construct a network, having given you the architecture? Anybody? What would I mean by that? learn all the parameters. So we saw how the same perceptron could compute an AND or an OR just by changing the weights. So in order to decide what the behavior of the network is, we have to decide what all of these weights and biases are. And so when we speak of constructing a network, we are speaking of determining what the weights and biases are. Now, one way to do it is to construct it by hand. For example, if I wanted to construct a network that had this diamond-shaped decision boundary with an output of 1 inside and 0 outside, then I know from basic principles that I could construct it by having one neuron each for each of these 4 boundaries, and then a final neuron that ORs the output of the 4. And a network such as this will compute this diamond-shaped decision boundary, and by sheer inspection, you can determine what the parameters of the various perceptrons are. The problem is this kind of handcrafting of a network can only be done if you already know what the function must be, and only for the simplest of problems. For something even just a little bit more complex than absolutely trivial, it is not feasible to be handcrafting networks. And so now, instead, what we want to do is to automatically estimate the multi-layer perceptron. So more generally, if I want to construct a multi-layer perceptron which computes some function g of x, then I want to, again, assuming that this MLP has the architecture to compute g of x, then I want to come up with some automatic technique that determines what the parameters of the network, what the weights and biases are, such that this network computes g of x. So how will I do that? Now, I'll be given g of x, which is some function, which is the function that I'm trying to model. So let's assume that this g of x is shown by this dotted line over here. And now I'm given the network. For any given setting of the parameters of this network computes some function, f of x semicolon w. So let's say for some setting of the parameters, the network computes this function shown by the red dotted line. Then clearly, the function that the network is computing in this case is not the function that you want it to compute, which is the blue dotted line. And there's an error between the two shown by this shaded region. And so when I want to construct this network to compute function g of x, what I want to do is to determine what the w here must be, so that this the area of the shaded region is minimized. Is that making sense? Okay, so that's basically what we want to do, right? Now let's put some math to it. In order to determine what the W must be to minimize this shaded area, again, this is all math. So first I need a formula for the shaded area, right? And the formula for the shaded area, the first thing I need to do is to compute the error between the function I want to compute g of x and the function that the network is computing, which is f of x semicolon w. So at every x, I need to be able to compute this error. And then the shaded area itself is simply the integral of this error over all of x. So it's the integral from minus infinity to infinity of the error between the function f, the network function f, and the target function g, integrated over all of x. And we want to determine the parameters w that minimizes this total error, this integral. And this integral, of course, is a function only of w, because as you change w, this red function changes, and so does the shaded area. So the actual task we want to perform is to compute the parameters w that minimize this integral. Is this making sense? Any questions so far? I'm going to assume that you know this, you understand this, right? But then, here's a problem. for me to be able to perform this kind of optimization, I need to know what this error is. I need to be able to compute this integral over all of x, which means that I need this function g of x to be specified for every x. Otherwise, I cannot integrate over the entire domain. And in practice, this means that g of x has to be known for every input x. And in practice, no such specification is going to be given. Your real life problem in real life, for example, this is like saying, I need to know the transcription of every possible voice signal that can ever be generated, or every possible image that can ever be seen. Now, this kind of specification is simply not going to be given to you. In fact, if g of x were fully specified, why not just simply use g of x? Why use a network? So we're not going to have such specification. So here's what we'll do. Because g of x is not going to be fully specified for every possible x, what we will do is sample g of x, basically. And in fact, in the most generic case, we may not even know the form of g of x. On the other hand, we will be able to compute the value of g of x at specific x's. And how does that happen? In real life, if the network I'm trying to train or compose is for classifying images, then g of x is this mythical function that perfectly classifies every possible image. And so, although I might not know g of x everywhere, I can sample it. I can provide it a bunch of inputs and compute the value g of x at those inputs. It's like saying, I'm going to get a bunch of images and find their class labels, or I'm going to get a bunch of speech recordings and get their transcriptions. When we do this, what we are really doing is, yes, exactly, getting these samples x and the corresponding value g of x. And so now, based only on these points, we no longer have the entire function. Based only on these points over here, which is pairs of x and g of x, we have to estimate the entire function. And therefore, here is the situation we actually end up with. We must learn this entire function g of x, shown by this mesh over here, from just these few examples, which are samples of g of x. These are our training samples. So here, we introduce the notion of empirical error. So when you're speaking of sampling, you're speaking of sampling the function. So meaning, I don't know g of x everywhere. So I'm going to give you the value of g of x at some values of xx. So this pair of x and g of x, this basically, I haven't written it here, basically for the value x at which you're computing g of x and the g of x itself, that together forms one training sample, right? And so what we will do is, we cannot compute this shaded area because we don't know g of x everywhere. Instead, we're going to take a bunch of samples, x's, and at each x, we will obtain the value of g of x, which I'm showing by this character d. And then what we will do is to try to estimate. So the network itself is going to compute some f of x semicolon w at each of these training samples. And so at each of these training samples, we can compute this error, which is the length of these red lines. And so what we will do is to try to minimize the average length of these red lines. And the expectation is that the average, if you minimize the average length of these red lines, then the shaded area will also shrink and become very small. X is an arbitrary input. My illustrations are two-dimensional or one-dimensional, but you have to think of this as some high-dimensional input, right? So instead of trying to minimize this integral over here, we will minimize instead the average error over all of these training samples. In other words, we're going to find the W that minimizes this average error, which we will call the empirical error. And the expectation is that if I minimize the average length of all of these red lines, the shaded area will also get minimized. Is that making sense? Right? So it's fairly straightforward. And so this is how we have modified our training paradigm. We want to find the network parameters W such that the average error over all of these training samples is minimized. In other words, we want to find the network parameters such that the network computes. So Nikhil, we'll get to that later, right? Such that the network fits these training points exactly. The function G exactly at all of these training points. And the hope is that if the network computes the exact value G at all of these training points, it will also compute the function G correctly everywhere else. And clearly, that's not a very good expectation that's not a very good expectation, but it's the best we can do. And so the story so far is that learning a neural network is the same as determining the parameters of the network required for it to model a desired function, assuming the network has sufficient capacity to model the function. Ideally, we would like to optimize the network to represent the desired function everywhere. However, this requires knowledge of the function everywhere. Instead, we draw input-output training instances from the function and estimate network parameters to fit the input-output relation at these training instances. And we hope that if we fit the function network correctly at these training instances, it will fit the function elsewhere as well. Any questions? Okay. Assuming no. So here's your first poll. Can everybody see the poll? Okay. Okay, 10 seconds, guys. All right, so let me stop the poll. So Sally, the function fx comma w is your neural network. And since you have your neural network, you can always give your neural network an input and it's going to compute an output. So f of x colon comma semicolon w can always be computed at any x. Does that answer your question, Sally? Okay. Deriving the structure is a much more challenging problem. There's a lot of work on it. And Arpit, by empirical error, we mean this, the average error over all of the training samples, which is our proxy for this shaded area. What we want to minimize is the shaded area. Instead, we minimize the average length of these red lines, the errors, and and hope that if you minimize that, the shaded area is minimized as well. Why do we assume? So slide 28. By function, what do you know by a function? A deterministic function is one that has a unique output for any input. That's why we're assuming that. Okay. What was the... So the idea behind the noise over here is that this is just an assumption that you don't actually have a perfect reading of the function that you're trying to compute, that there may be some noise. That's all. Typically, we ignore the noise. A generative model is deterministic functions. The network is deterministic. What goes in is not. We'll get to that if you're thinking of generative neural networks. Generative statistical models are a different kettle of fish. We'll talk about it much later in the course. Let me continue, right? So over here, first question, true or false? False. And the second one, is the first statement right? Second, third, fourth. The fourth one is no, right? So neural networks are universal approximators. Any network of any architecture can approximate any function. No, we need sufficient capacity. And network architecture must have sufficient capacity. The neural network is actually a parametric function whose parameters are its weights and biases. And the parameters must be learned to best approximate the target function. So let's begin with a simple task. Learning a classifier. We're going to work with classifiers because it's simpler than regressions. And also because this was among the earliest problems addressed using MLPs. Specifically, I'm going to consider binary classification. Now, the binary class, consider a simple binary classification where the output is either class 0 or class 1. If the output is either class 0 or class 1, then how do you count an error? You have the truth, you have the function g of x, which outputs either a 0 or a 1 for any input. You give it any image, it says whether it's a cat or not, right? And then you have the function f, which is your neural network, which produces a binary output 0 or 1 for any input. What is the error metric in this case? The obvious error metric is if the classifier is right or wrong. So if f of x is exactly equal to your desired output d, which is g of x, there's no error. And if it's not equal, then there's an error. So it's the percentage of wrongly classified training points, exactly as Aviral mentions. So this is what we want to minimize. We want to train the network to minimize this average classification error, right? Let's start with the original MLP as proposed by Rosenblatt or Minsky. This is a network of threshold activation perceptrons. How do we train such a perceptron, such a network? Again, each perceptron over here first computes an affine function of the inputs and passes it through a threshold function. We know this, right? Now, the simplest MLP is just not multi-layers, it's just a single perceptron. So a single perceptron, as we all know, has a behavior of this kind. The affine function of the inputs is passed through a threshold activation. So there's a linear boundary. The function computes an 1 on one side of the boundary and a 0 on the other side. So if the input were two-dimensional, the function it computes is going to look like the step function. In reality, of course, the input is going to be many-dimensional. This is just for illustrative purposes. So now you want to compute, you want to learn this function. There's a ground truth. Let's assume there's a ground truth function which is given by the step function. But you don't really have this function g of x. Instead, you must learn it from training samples, these green and red dots. And so from just these training samples, you have to learn the parameters w and b that give you the correct Heaviside step function. Is that making sense? Yes or no? Okay. So from just these training points, we need to learn the weights and the bias so that we learn the correct function. Now, again, I'm going to restate this perceptron as before by adding an extra input which is pegged at 1 so that the bias becomes just a weight. And so when I think of it this way, with this extra input pegged at 1, then we say that you first compute a linear function of the input, which is to say a weighted sum of all of the inputs. And this perceptron outputs a 1 if this weighted sum of inputs is positive, and outputs a 0 otherwise. And in this case now, now that you've restated it and stated it in this manner, the decision boundary is where summation wi xi is exactly equal to 0. So now it's a hyperplane to origin. So these w's are what we want to estimate. This making sense? Okay. So here's what we have. You're just given a collection of training points, these red and blue dots. And we want to find the hyperplane summation wi xi equals 0. That's the equation for the hyperplane that perfectly separates the two groups of points. And again, we're assuming that the points were selected from this function, from an actual step function, which means that there is a step function, there is a linear boundary that exactly separates the red and blue dots. So we're assuming that the dots are actually, the data are actually linearly separable, meaning that there is a linear boundary, a hyperplane that separates the two classes. Now, the boundary is given by summation wi xi equals 0. I can rewrite that in vector format. I can put all the weights w into a single vector. The input, of course, is a vector. And so I can write summation wi xi as simply an inner product w transpose x. And so saying summation wi xi equals 0 is the same as saying the inner product between the vector w and the vector x equals 0. So when you say something of this kind, what is the relationship between the two vectors w and x? Can anyone tell me? Orthogonal, right? So what does this tell me? This is basically the equation. This equation is represents the set of all x's that are orthogonal to the weight vector w. And so when the weight vector, whatever the weight vector is, the decision boundary is going to be perpendicular to the weight vector. Because by definition, we are saying that this boundary w, because you're given the weight vector w transpose x equals 0 represents the plane which consists of all the vectors x that are orthogonal to w. And so now, when I speak of learning my perceptron, I want to find the weight vector w such that the plane described by w transpose x equals 0 perfectly separates the red and blue classes. Now, there are various ways of doing this. The original solution proposed by Rosenblatt was an online algorithm, the famous Perceptron algorithm. It initializes the weight w somehow, and then incrementally updates it each time we encounter an instance that is correctly classified. And if the data are linearly separable, it's guaranteed to find the correct solution. So here's how the Perceptron learning rule works. You cycle through all of the, you initialize your weight vector somehow, and then you cycle through all of the training instances, and then only update the weight vector on misclassified instances. Now, now here's something interesting over here. When I look at w transpose x equals 0, what is w transpose x in general? When I look at a general w transpose x, forget about equals 0. When I say w transpose x, what is w transpose x? Can anybody tell me? What exactly is it? The dot product. How do you compute it? So let me just stop sharing my screen for a bit, and I think I should share my screen with a notebook if I can. So can you still see my slides? Yeah. So I'm running slower than I should. Please bear with me. It's whiteboard. And this comes up. Give me a second. So, oh no, please. Okay. So when I have a weight w, right? Say this is w. And then I have x, a vector x. What is w transpose x? W transpose X is going to be mod W, mod X, length of X, length of W, cos theta. Do you remember this? Right. Okay. So when will this be positive? When will this be positive? When the angle is less than theta. And when will it be negative? When the angle is greater than, when the angle is less than 90, and it will be negative when the angle is greater than 90, right? So now going back here, suppose I have a positive instance. Suppose this instance belongs to the positive class. Actually, think of it this way. Suppose I have a plane of this kind and I have a vector W. What will W transpose X be? What will the sign of W transpose X be for the data points on this side of the plane, on the same side of the plane as W? What about the points on the other side of the plane? Negative, right? Because the angle is greater than 90. So now, suppose I have an instance of this kind, which belongs to the positive class. And I want to find the best possible weight vector for it so that it's guaranteed classified positive. Which is the direction in which the weight vector must point? Anyone? So let's say, suppose, so I have my axis, right? If I have a vector over here of this kind, and this is my x, then if the x belongs to the positive class, then I want the decision boundary to be perpendicular to the x. It should point directly at the data point. And similarly, if x belongs to the negative class, which way must x point? Exactly opposite, correct? And that is the basic idea behind the perceptron rule. Suppose I have a positive instance and my current estimate of the weight is misclassifies it, then I try to drag the weight vector in the direction which is best for that particular data point. I add x to the weight vector. And on the other hand, if I misclassify a negative instance, I try to push the weight vector in the direction that's most appropriate for that data instance. I subtract xi from the weight vector. So is the logic behind this making sense to you guys? So Mohammed, what did you not get?
The direction, where you were explaining about the direction.
So this one, right? So if this is a positive instance, x, right? Then
Yes.
cos theta will be 0 if the weight vector points directly at x, correct?
Okay.
Whereas if I have a negative instance, if x belongs to the negative instance, then cos theta will be 180 if the weight vector points directly exactly away from x, right?
Yeah.
And we saw that W transpose X is basically considering cos theta, right?
Yes.
So you want the weight to point directly at X to make sure that the decision boundary is as far away from X as possible. If X is a positive class, you want it to point directly away from X to make sure that the decision boundary again is as far as possible if X belongs to the negative class, right? That makes sense? Yeah, okay. That's basically what we do. And so there's a lot of arithmetic over here. Skip the arithmetic. Let me show you how this works visually. Let's say these are all my data points, right? I'm going to randomly initialize my W. That's going to give me this weight W, and this is my decision boundary. I check all of my training data instances, and I find this negative instance is misclassified. So that is the negative instance. So obviously, the ideal decision boundary, the ideal weight vector for this negative instance is going to be pointing exactly away from it. So that's going to be minus of this negative instance. So I'm going to subtract this vector from W. And that gives me my new W. And that gives me my new decision boundary. Then I check all of my training data points again, and I find that this positive instance is misclassified. And for a positive instance, I want the weight vector to point directly at the instance. So I add the positive instance to my weight vector. That's my new weight vector, and that's my new decision boundary. And now all of my training data points are correctly classified. There are no more updates to be done. And I'm done. So did this make sense? If the classes are linearly separable, that was the beauty of the proof, then they are guaranteed to converge in a finite number of steps. And we'll put up the reading for this, but it's a very simple proof. And in fact, you can compute the boundary in a single step if you're not doing this in an online manner. And the mechanism is also shown on the slides. But then here's the problem. When the classes are not linearly separable, for example, if my training data points are like so, then there is no hyperplane that cleanly separates the blue from the red points, right? So, Logan, I don't know what your name is, but this is just one of the. There are many different solutions. The best way of doing it is on the slides. Take a look. The point we are trying to make is slightly different here. First, when the classes are not linearly separable, is the perceptron always going to be 1D? What do you mean by that? Can you explain, Saidi? This is the vector, the data can be in any number of dimensions, right? And the weight vector is going to be a vector in that in that dimensional space. The vector is just a single vector. Weight vector is just a single vector. Yeah, so the problem is that if the data are not linearly separable, then the perceptron algorithm will never converge. It's going to keep chasing the errors because there's always an error. They're not linearly separable. But even so, then there is a way of computing a minimum error solution. But the point is that we need to know how the data are labeled for us to compute the boundary. Now, but that's for a single perceptron trying to learn a single linear classifier. But then consider a problem of this kind. This is the double pentagon problem that we just saw. Let's say I want to learn an MLP for this function, which computes outputs of 1 inside the yellow regions and 0 outside, except that I'm not given the function, I'm only given these data points, these red and blue data points. And just from these red and blue data points, I need to compute the network that perfectly computes this decision boundary. Now, I know that this network over here, which has 5 neurons for the first perceptron, this subnet for the first pentagon, this subnet for the second pentagon, and a final OR. I know that there's a setting of weights for this network that will exactly compute this decision boundary. So this architecture is sufficient. But then let's see how I can compute the parameters of this network using this data. So even using this perfect architecture, can I use the perceptron learning rule to learn the classification function? Now over here, we need the lower level neurons to learn all of these boundaries. We know that all of the lower level neurons are linear classifiers. So for a neuron, as we just saw, for a neuron to be able to learn the boundary, we need the data to be linearly separable, right? And so each of these neurons will need linearly separable data in order to learn the boundary. Unfortunately, if you look at the labels given over here, is there any boundary over here Is there any set of data that are perfectly linearly separable by any of these boundaries? No, right? So for example, if I wanted to learn this first neuron, that neuron has to learn this boundary. But then from the perceptron rule, we saw that for it to be able to learn this boundary, you want all the data on one side of the boundary to be colored red and all the data on the other side to be colored blue. But we don't have that. And so then what is our problem? How do we solve this problem? Any ideas? You cannot. If the data are not linearly separable, you cannot learn this perceptron, right? What we need to be able to, increasing dimensions doesn't help, because so increasing that, these are not linearly separable classes, right? What we will need to do is to relabel some instances so that we can learn this line. For this line to be learned, we need all of these points on this side of the line to be relabeled red, and all of the data on this side of the line to be kept blue. And if we relabel the data in that manner, then we could learn this line. Does that make sense? Any questions? Okay. So in that case, we'll have our next poll. Let me. Can you see the poll? Harpreet, they may be linearly separable in some higher dimensional space. You don't know what that space is. You don't know what the transformation to take it to that space is. So can you guys, are you not able to see the poll? All right, 5 seconds, guys. Well, let me stop this poll. So for this first question, what is the answer? No. What about the second one? Is the first statement. Perceptron learning will require linearly separable classes to learn the model that classifies the data separately, but the data are not linearly separable. Is this true? It will require relabeling the data to make them linearly separable with the correct decision boundary. Also true, right? And so this is the situation we have. In other words, let's just assume that I just magically have all of these neurons that have been correctly learned, right? If all of these neurons have been correctly learned, and I have the correct parameters for all of these neurons, all I need to do is to learn this one final neuron so that I get the perfect decision boundary. Can I learn this neuron from this data? Yes or no? Everything else is perfect. Will I be able to learn the neuron? I cannot learn the neuron from this data, right? What will I need to do? I need to relabel, but do I know how to relabel the data? So I'm telling you that there is a network that can perfectly classify these data. I'm also telling you that all of these perceptrons have already been correctly set. How would you go about learning this neuron? You'd have, if there are n training instances, because we cannot see the data, you'd have to inspect every one of the 2 raised to n minus 1 ways of relabeling the data. Learn a perceptron with that relabeling and check if the overall network classifies your entire training data correctly. Is that making sense? Inefficient indeed, right? So the point is, I know that the data points have to be relabeled, correct? So I just don't know which ones. And so what I would have to do is to check every possible way of relabeling all of my training data until I find one such that when I learn the boundary using that relabeling, the overall network does a perfect job. And if I have n training instances, each of them can belong to class 0 or class 1. So there are 2 raised to n ways of relabeling the data. This is just with one training instance, with one perceptron, right? So yeah, you must learn the boundary and then check if the overall network now is perfect on the entire training data, right? So this one individual classifier will actually need the kind of relabeling over here. And this is not given, so you have to inspect every possible way of relabeling the data. So this means that in order to learn just this one boundary, this one perceptron, you're not merely learning the perceptron, you must also learn the labels for all of the lower units. Now, of course, that's just for a single line, right? For a single perceptron, you have to try every possible way of relabeling all the dots, such that we can learn a line that keeps all the red dots on one side, right? So relabel to change the boundaries and no, so you're going to relabel the data just to learn this one perceptron, right? And then once you've learned the perceptron, you're going to pass your entire training data through the network to check if all of the training data are correctly classified. If they are not correctly classified, then you know that this boundary is incorrect. Then you'd have to go back and relabel them all over again. And you'd have to try this every one of the 2 raised to n ways, right? That's just with one neuron. When none of your neurons are given, right? Here we assume that every other neuron was given to you. In reality, none of them are given to you. So what would you do? You'd have to find out how to relabel the data for every one of the neurons, such that when they're all set according to that labeling, the overall network does the right job. So each neuron is going to search over 2 raised to n possible relabelings. There may be k neurons. And so you're going to be searching, exactly. It's an exponential search. This is not going to happen in any reasonable amount of time. And so individual neurons represent one of these boundaries that compose the figure. We must know the desired output of the neurons for every neuron, for every training instances in order to learn each neuron, which means that each of the neurons over here must see a specific version of the data that's correctly relabeled. And so we have to sort of search through the correct way of relabeling the data for every one of these neurons, such that each neuron is looking at a linearly separable classification task, such that they all combine to form this double pentagonal precision boundary. And if any one of these neurons uses the wrong relabeling and is incorrectly learned, then the overall network is not going to do the correct job. So this means that training this network using the perceptron rule is a combinatorial optimization problem. We don't know the outputs for the individual intermediate neurons. So we must also determine the correct output for each neuron for every training instance. This is exponential in time complexity, right? Even a convex hull, it's going to be exponential, right? Basically, you're going to check every way of labeling. You're going to check all 2 raised to n ways of relabeling the data for neuron 1, all 2 raised to n ways of relabeling the data for neuron 2, and so on for every one of the neurons. Then you learn the boundaries using the relabeling and check if the overall network is correct on the entire training data. If it's not, you have to redo the entire process. It's an exponential search. Yes, right? And so this is not going to work. And this was discovered in the 50s. So we had these greedy algorithms called Adeline and Madeline. Once they've realized that the perceptron learning rule cannot be used to learn an MLP because of the exponential complexity of assigning intermediate labels, we need alternate methods. And so these greedy algorithms called Adeline and Madeline were proposed by Bernie Widrow, who's still alive, who's still a legend. And they are based on a learning algorithm called the delta rule that we still use all over the place. Adeline and Madeline are on the slides. Please check them out. They will appear in the quiz. But anyway, the story so far is that learning a network is the same as learning the weights and biases to compute a target function. It requires a network with sufficient capacity. In practice, we learn networks by fitting them to match the input-output relationship of training instances drawn from the target function. A linear decision boundary can be learned by a single perceptron with a threshold function activation in linear time if the classes are linearly separable. Non-linear decision boundaries require networks of perceptrons, and training an MLP with threshold function activation perceptrons will require knowledge of the input-output relation for every training instance for every perceptron in the network. This must be determined as part of the training. So for threshold activations, this is a combinatorial optimization problem with exponential complexity. So did this make sense? Any questions so far? So Sally, a perceptron is a linear classifier. So to learn it, it has to see linearly separable data, right? Non-deterministic polynomial complexity. Basically, it's something in complexity theory. The point is that if I tell you this is the labeling, you can verify it in polynomial time, but to find the correct relabeling takes an exponential search, right? A single relabeling can be, you can learn all the boundaries for a single relabeling very quickly, because those are computed very fast in polynomial time. But then you have to search through an exponential number of relabels. Any other questions? Okay. So the realization that training an entire MLP was a combinatorial optimization problem stalled the development of neural networks for well over a decade. Now, the problem is because of this, our binary error metric is not useful. So look at this. Let's say that the ideal function I want to learn is this blue dotted line, right? Which outputs a class 0 for anything to the left of this boundary and class 1 to anything with the right of this boundary. And I'm trying to learn these from these 5 training points, right? Now, it's a linear classifier. I'm assuming, let's say I have a linear classifier. Then for a linear classifier, then the decision, what is a linear classifier in one dimension? Anyone? What's a linear classifier in one dimension? It's just a threshold. It's a threshold. So you'll say anything to the left of the threshold is 1, anything to the right of the threshold is 0, right? The parameter is the threshold. Now let's say that your initial estimate for the network for the classifier was given by this red curve, right? So how many errors is the function making? Over here, 2. How would you modify the function? By changing the threshold, right? Now, if I move at this point, if I move the threshold slightly to the right, will the error change? What about if I move it to the left? Because just wiggling the things, this guy left or right over here, is not going to change the output of the function at these 2 points. And so the classification error will not change. So this means that just counting the classification error at a particular parameter setting doesn't tell you in which direction the parameter must be modified to improve the function. Is that making sense? It's useless to move it unless it actually moves past a training point. So the reason for this is that the perceptron, so this is in 2 dimensions, right? In 2 dimensions, let's say I'm trying to learn to classify these red and blue dots. And let's say my initial estimate for the model is this blue curve. I can wiggle this blue line. I can wiggle the blue line all the way up to here in this direction and all the way up to here in this direction without actually changing the classification error. So wiggling the weight doesn't tell you whether I'm wiggling it in the correct direction or not. The perceptron is a flat function whose derivative is 0 everywhere except at 0 where it's non-differentiable. That's the perceptron's threshold activation. What this means is that I can vary the weights of the perceptron quite a lot. I can vary the weights so that the decision boundary swings all the way from here out to here without actually changing the classification error. And so if I vary the weights and count the error, this error doesn't give me any indication of whether I'm varying the weight in the correct direction or not. And if I go to larger problems like this one, it only gets worse. Individual neurons can change significantly without changing overall error because the MLP is a flat non-differentiable function. What I mean by this is that I can change all of the parameters of the network to a significant amount in different directions. And unless the overall decision boundary crosses some training point, I will not know. The error will not change, and I will not know if I'm moving things in the correct direction or not. So let's change our approach. Instead of simply counting the error, such that let's the error such that modifying the classifier slightly lets us know if we're going in the right direction or not. For this, we need to do two things. We want to change our activation function and the manner in which we evaluate the mismatch between the classifier output and the target output. Now, our mismatch function will not actually count errors. It will count a proxy for it. So in our perceptron, instead of using a threshold activation of this kind, I'm going to use a different activation which has non-zero derivatives. So threshold activation has 0 derivative everywhere, except at 0 where the derivative is undefined. Instead, I will have activations of this kind, which have non-zero derivatives over most of the space, such that a small change in weight can result in non-negligible changes to the output. And this enables us to estimate the parameters using gradient descent. To see why, let's look at this figure. Again, here is my binary classification problem in 1 dimension. So if my current function, if I were using a single perceptron with a threshold activation, if my current parameters had this threshold, if I slid the threshold all the way back to this point, the total number of errors remains unchanged. So although I'm moving the threshold in the correct direction when I go from T1 to T2, if I look at the total count of errors, I get no indication that I'm going in the correct direction, right? Instead of having a threshold activation, suppose I had a sigmoid. And instead of simply counting errors, I counted the distance from the function. So over here, the error was basically the distance from the function, even in this case, right? But basically, we're saying, was it classified correctly or not? Instead, I'm going to compute the distance from the function. So over here, a sigmoid is still just a smooth version of a threshold activation. Instead of going directly from 0 to 1 at the threshold, it slides from 0 to 1 and hits 0.5 at the threshold. So now, the error I'm computing is the distance from the data point to this curve. the total length of these dotted lines. Now, the actual classification rule is going to say the output will be called class 1 if the value of the function is greater than 0.5, and it will be called class 0 if the value of the function is less than 0.5. So this function and this function are making the same number of errors. That making sense? Can you see? Okay, and so also, right. On the other hand, instead of counting errors, suppose I count the total distance, the length of these dotted lines. Now, if I move the function backwards from t1, so such that it instead of crossing over at t1, crossing 0.5 at t1, it crosses the 0.5 threshold at t2. Has the number of errors changed? The number of errors is still the same, right? Because everything to the right of this 0.5 is being called 1, everything to the left of this 0.5 is being called 0. But what about the total length of the dotted lines? Has that increased or decreased? It has decreased. So now, by changing the way in which I am computing the error, I now have an indicator. Although the error has not decreased, this total length of the dotted lines, which is my proxy for the error, it's not the error, it's a proxy for the error, that has decreased. And so now I know that I'm moving the function in the correct direction. So that is what we're going to use. And to exercise your understanding of this concept, we're going to have our third poll for the day, which is this one. Can you all see the poll? You get 45 seconds. Five seconds, guys. Okay, let me stop the poll. So for the first one, which of the following are true? Increasing or decreasing the threshold will not change the overall classification error, true or false? Yes. You cannot know if a change of the threshold increase or decreases moves it in the correct direction that will result in a net decrease in classification error, true or false? True. The derivative of the classification error with respect to the threshold gives us an indication of whether to increase or decrease the threshold, true or false. For threshold activation, there is no derivative, right? So what about the continuous activation? Shifting the function left or right will not change the overall classification error unless the crossover function moves past a misclassified training point, true or false? It's true, right? But shifting the function will change the total distance of the value of the function from its target value, true or false? True. The derivative of the total distance with respect to the shift of the function gives us an indication of which direction to shift the function to improve classification error, true or false, right? You say that if I move it in this direction, the error is decreasing. So the derivative is negative. If the error is decreasing, it gives you information. So these are all the true ones. So let's go back to our problem, right? Instead of simply computing the error over here, you have to pick your activation function, Sally. There are ways of defining more complex activation functions that appear to be learned, but they're also composed of basic predetermined activation functions. We'll talk about that in later time. So anyway, so instead of simply having a binary, are they the same or are they not? We're going to instead define a proxy for the error called the divergence. And the divergence function has the following properties. If the two functions are identical, then the divergence will be 0. If the two functions are not the same, then the divergence will always be positive, regardless of which direction, which one is greater than the other. Also, if I have the divergence of between f and g, I want divergence of f comma g to be differentiable with respect to f. So the divergence function is a measure of the gap between these two functions that has these three properties. It's 0 if there is no gap, it's positive if there is a gap, and it's differentiable with respect to the red dotted line. This divergence function quantifies the mismatch between the network output and the target function. So for classification, this is not a classification error, but a proxy to it. And so, how do you learn a network? When the function has the capacity to represent the network, instead of the error, what we will now integrate is this divergence function. You're going to, the shaded region is now the integral of the divergence function over the input x. And so basically in the case of but that's the divergence function number one, that measures the error. But now we want the second thing to go with it. We want to change the activation function over here. We're going to replace the threshold activation function with functions that have continuous gradations, like a sigmoid, a ReLU, or the soft plus. These activations are differentiable almost everywhere. They have derivatives almost everywhere, and they are continuous and they are graded. So even if they're not differentiable, like in this corner for the ReLU, we have something called subderivatives, which we will talk about in a later class. The key point is that it's continuously graded, and that it's continuous, it's graded, and it's differentiable almost everywhere. So one particular activation that's really useful is the sigmoid, which looks like this. We've seen this a few times. And the reason the sigmoid is interesting is that it can be viewed as the probability that the output y takes the value 1 given some x. So consider this problem. Suppose I have a two-dimensional example where the data are not linearly separable. So I have some red points on the blue line, some blue points on the red side of the line. So if I plot it, I have some red dots hanging over here, some blue dots on the floor over there. There is no hyperplane that cleanly separates the two colors, right? So in one dimension, if I have non-linearly separable data, you're going to have data of this kind. So here a linear separator is a threshold. No threshold will cleanly separate red and blue dots. But then let me look at it differently. Let's look at a small window around each point. So at this point, I take a look at a small window around it and plot the average y value within that window. That's going to be 0 out here. Initially, it's going to be all 0. But then when I begin hitting regions where I also have some instances where the y value is 1, the average y value is going to go up off of 0. And as I keep going right, that average is going to go smoothly up from where it's all 0 to where it's all 1, and it's going to swing up in this manner. So at each point, this guy tells you what is the average y value of all the training data points in a small region around this x. So in other words, it's the expected value of y within that region, which is also the probability. What fraction of instances took the y value 1? So that's an approximation of the probability of y being 1 at that point. So if I simply count the average value of y within each window, that's probably going to look like this. And that's actually p of y equals 1 given x. Is this making sense? Dheeraj, we don't really know what error is. So the only thing that we have for the divergence from a mathematical point of view is that it needs to be continuous, and the assumption is that if the divergence is large, the error is large. The divergence is a quantifier. So why did we have to change the activation? That goes to this, right? Here the activation became a sigmoid. If I was still using a threshold, the fact that I'm using the distance didn't really make a difference, right? Okay, so, all right. Anyway, going past of this, so this guy here, it turns out the sigmoid actually captures that shape very nicely. We'll talk more about it in a later class. And in a two-dimensional case too, problem 2, it has the same property, right? We'll return to the fact that perceptrons with sigmoid activations actually model class probabilities in a later lecture. But for now, moving on, what happens is that if the activation is differentiable, then here's what happens. This sigma is differentiable, right? So now I know how much a small, because it's differentiable, what does it mean for a function to be differentiable? It means you're able to say how much a small perturbation of the input will perturb the output. And so if this activation function is differentiable, I can tell you how much a small perturbation of z will perturb y. Now this over here is an affine function. That too is differentiable, right? So I can tell you how much a small perturbation of w is going to perturb z. And so I can tell you how much, and because I can compute how much a small perturbation of z will perturb y, by chaining the two, I can tell you how much a small perturbation of w will perturb y. And so this entire perceptron ends up being differentiable, not just the output of the perceptron ends up being differentiable, not just with respect to z, but also with respect to the inputs and the weights. Is that making sense? Okay. And so, what does that mean? Because this perceptron is differentiable, right? When I change this activation to be differentiable, I can tell you what dy over dz is. I can tell, and because that's just sigma prime z. And then I can tell you what dy over dx is, because that's sigma prime z times dz over dx, right? So it's just a chaining of minor influences. And so because of that, now if I go to the larger network, I can tell you how much a small perturbation of this weight will change the output of this perceptron. But because the activations are differentiable, I can now tell you how much a small perturbation of this output will change this output. And how much, similarly, how much a small perturbation of this guy will perturb this guy. And because this one is differentiable, I can tell you how much small perturbations of these terms will perturb the y. So as a result, I can compute overall how much a small perturbation of w will perturb y. The entire network becomes differentiable with respect to every one of the parameters of the network. Is that making sense? Right. That's the beauty. And so the overall function, the network is a function, right? This overall function is differentiable with respect to every parameter in the network. We can compute how small changes in these parameters will change the output of the network. The actual formulae will derive later. So now going back here, when this function, let's say my network function has the capacity to exactly represent g of x, I'm going to replace the error by this divergence function. And I'm going to now compute the shaded area as the integral of the divergence function over all of x. But then I'm going to make one more update. Remember that my network is an approximator. It's never exact. So that means I get to have some trade-off. I improve the approximation in some places at the cost of the approximation in other places. Now, suppose I observed that my input x never takes these extreme values. Should I be wasting any effort trying to minimize the error in these regions? Doesn't make any sense, right? You want to focus on the the regions of the input that are actually seen, that are actually important. And so what we will do is to weight this divergence by the probability that that particular input X actually occurs in real life. And so instead of simply taking the integral of the divergence, you're going to multiply the divergence by the probability at any X by the probability of X and then integrate. And so what is this term? What is this integral? That is just the, I'm going to go a couple of minutes over, right? So that's just the expectation. And so what we want to do is to find the weights that minimize the expected divergence between the network function and the function you want to estimate, the function you want to model. But then going back, we don't really have the function g of x, so we sample g of x, right? But we want to sample the g of x so that we naturally see more instances of more probable x's and fewer instances of less probable x's to get the proper weighting. But guess what? If you simply naturally sample from real life data, you're just naturally going to get more instances of more probable x and fewer instances of less probable x. So the whole thing just fits. And so this gives us our empirical risk. The expected divergence is this, as we saw. So we saw that the expected divergence is the integral of the divergence, the probability weighted, the integral of the probability weighted divergence over the entire input, which is basically the average divergence over the entire input space. Instead, we are going to use the empirical estimate of the expected divergence, which is the average divergence over all of your training samples. And as we will see later, this average divergence is actually what is called an unbiased estimate of this guy. And so our hope is that by minimizing this average divergence, which is to say that we saw the figure earlier, the average length of these lines will actually minimize the shaded area. And so we end up with a problem of what's called empirical risk minimization. You'll be given a collection of training input-output pairs. We start off with some way of quantifying the error on any input, which is by defining a divergence function between the output of the network and the desired output of the network. Then we define an empirical risk or an empirical average divergence, which is the average divergence over all the training samples. And then we want to estimate the network parameters to minimize this average divergence, which is fine, because all the samples are given, the only variable that remains is the other parameters. So this is just a function of the network parameters. And we find the network parameters that minimize this average divergence, which we also call the loss. So again, I'm calling it a loss. It's just a measure of error. The standard terminology is loss. Second, the empirical risk, loss of W, is only an empirical approximation to the true risk. This expectation is what we actually want to minimize. But what we will minimize, what we do minimize in practice is this loss. And this loss is only a function of the network. So here is the overall problem statement. You're given a collection of training input-output pairs. You define a loss function, which is a function of network parameters, which is the average divergence over all of your training samples. You minimize this with respect to the network parameters. And if you do, then hopefully you minimize the error at all of these training samples. Ideally, you make no error at any of these training samples. And then you hope that if the network fits these training samples, it fits the function everywhere else as well. And so the story so far, just to wrap up, we learn networks by fitting them to training instances drawn from a target function. Learning networks of threshold activation perceptron involves solving a hard combinatorial optimization problem. Instead, we use continuous activation functions with non-zero derivatives. And this enables us to estimate network parameters. It makes the output of the network differentiable with respect to every parameter. The logistic activation function, the sigmoid, actually computes the a posteriori probability of the output given the input. We define a differentiable divergence between the output of the network and the desired output, and a total loss, not an error, which is the average divergence over all training samples. We may optimize network parameters to minimize this loss. This is empirical risk minimization. And again, this is a function. This is a function of W. So what we end up with is an instance of function minimization. We'll talk about how we do this in the coming classes. I apologize for going over a bit. I spent a little too much time in the early portion of the class.